Charles is not able to connect, but it will be no problem because we did the work together. So I will give the presentation on behalf of him. And so I'm going to talk about above ground and buried pipelines and what we have to consider for the seismic design of these two types of pipelines. So I would like to go through the different chapters again, similar to the one that Roberto presented. And at first, we have to think about what is needed and what is the scope for the different pipelines. So we have to consider continuous pipelines in this part 4, and the materials that are covered, similar to the silos and also tanks, are steel, unreinforced concrete, and reinforced concrete. The seismic actions that we have to consider are transient and permanent ground deformations. So transient deformations are related to wave propagation within the soil, and permanent ground deformation can be different. So we have fault crossings, settlements, liquefaction, and other phenomena that we have to cover within part 4. So what is the design concept for pipelines? First of all, as I mentioned in the morning, pipeline systems are not only the pipeline itself. So we have also to consider, let's say, the installations, some pumps and so on. So this is important to take into account. Furthermore, as you see here on the right, we have to consider also that we have straight pipelines, or parts of straight pipelines, and we have also banded sections. And these banded sections are the critical sections for the safety verification. And we have to consider these banded sections in a particular way. Furthermore, we have to take into account that we have to consider 3 components of seismic actions, and we have also to take into account the variability of ground motions, because there is a difference between a pipeline system and a usual building, because the pipeline system is continued over large areas, over maybe hundreds of kilometers, with changing soil conditions and with changing seismic actions. And that's what we have to take into account. Therefore, we need to take into account local side effects and incoherence for the seismic design. Furthermore, we have to think about how can we incorporate differential displacements due to the structural response of the substructures, because at first we are talking about above ground pipelines, and there is an interaction with the substructure. So there is also the need to calculate differential displacements along the pipeline. And we need also to consider, let's say, dynamic interaction effect with the installations that are also shown here on the right side. We have also sometimes some stations for, let's say, increasing the pressure. And these stations are also connected with the pipelines. And this is the points of these pipeline systems. So as I mentioned before, we need also to consider other materials. So it is the same. So the same principles that I'm going to present can also be applied to other materials, although they are not detailed described in the Eurocode concept. So we only have design rules readily available for steel and reinforced concrete and pre-stressed concrete pipelines. And we have also to take into account, as mentioned before, the ancillary elements like valves, pumps, instrumentations, and so on. So how can we carry out the design for above ground pipelines? So the ductility classes are limited to ductility class 1 or 2, but as for silos, for substructures, it is allowed to choose one of the ductility classes, DC1, DC2, or DC3. So we have 3 ductility classes that we can take. The design for permanent ground motion should consider the following induced permanent ground deformations. So first of all, we have to consider fault crossings, then liquefaction-induced phenomena. And these liquefaction-induced phenomena are important, especially if we have pipelines close to facilities, because facilities are usually located close to rivers. And then we have also somehow the problem with liquefaction-induced phenomena. Furthermore, there is another aspect to be considered. It is the slope stability topic in a topic. So it is not regulated in part 4. It is just mentioned that it is necessary if you have problems with slope stability along the pipeline, you should consider it, and then the design concepts are given in specific Eurocode codes that can be applied for these specific loads. Furthermore, we have also to consider landslides and local soil settlements. So local soil settlements are important because if we have, let's say, a settlement at one foundation, this will influence the pipeline, because then we have differential displacements between the different foundation points. And landslides are well known, so they are quite critical. So we saw it during the last flooding events. So even in Germany, we had a lot of problems with landslides induced soil settlements, and this is something that we have to consider. So here the figures are showing the effects of such differential displacements due to permanent ground deformation. So the question is arising how we can model the above ground pipelines. The easiest way is to say, okay, it is more or less a straight pipeline. The straight pipeline can be considered as, let's say, straight if the curvature is 20 times of the outer diameter of the pipeline. So, and these straight pipelines may be utilized with beam models and distributed masses along the pipeline. So this is quite clear. So this is a simple way of modeling. If we have elbows or let's say bends that are critical, somehow it's reasonable to incorporate special elbow elements or shell elements instead of beam elements in order to account for, let's say, the local effects that can occur within the bend due to buckling or also warping, which can occur in the area of the bend. Furthermore, the foundation should take into account soil structure interaction effects. And of course, the basic things, we have to take into account the strength, damping, pipeline geometry, stiffness and mass properties. And also we have to take into account the correct weight of the pipeline, so the mass of the fluid inside the pipeline, the dynamic characteristics of the substructures. And this is also a crucial point, the connection between the pipeline and the substructure. So sometimes we have a special connection in order to avoid, let's say, effects due to the temperature expansion. And therefore, we have some sliding capabilities, and there is no let's say, a possibility to take the seismic forces. So we have some, let's say, fixed supports and some sliding supports that should be taken into account in our calculation models. So the structural analysis is based on the force-based approach. As I already mentioned, this is a standard procedure in part 4, but a displacement-based approach is also applicable by nonlinear static analysis for the supporting structures. So there's no reason against it, but we have to keep in mind that we have to handle the differential displacement that can occur between the different parts or along the pipeline. Furthermore, it is quite reasonable to apply imposed displacements in case of permanent ground motions and to carry out a static analysis with equivalent, let's say, equivalent forces or equivalent displacements, and then to analyze what will happen. So this is usually only possible, for example, for fault crossings. So I will show some approaches during the next slides. So how can we combine the combination of actions? So from the practical point of view, we have to distinguish between non-pressurized and pressurized pipelines. And if we have pressurized pipelines, we have to take into account the internal pressure, and we have to add this load case simultaneously along the pipeline, and it should be superimposed with the seismic design situation. Furthermore, we have to consider also self-weight and further variable actions which can be caused by installations. And then we have to superimpose both the design, the seismic design in the seismic design situation, both the seismic actions as well as the static actions that are acting on our above ground pipeline. So what about the behavior factor that can be used within such calculations? We have, again, to distinguish between the different materials. First of all, we have welded steel pipelines, and we have to apply, or we can apply, ductility class 1 and 2, what we can see here. We have a different combination of behavior factors as defined in part 1.1. So this is QR for load redistribution. Then we have QS for overstrength and ductility, QD. So in the end, we will come up with Q factors between 1.5 and 3, depending on some geometrical parameters. So to apply it, we have also to consider reinforced concrete as a potential material. And the Q factor here can be taken to 1.5. And in case, of course, of unreinforced concrete, it's only allowed to apply 1.0 because, the deformation capacity and the capacity to absorb energy is rather low. It's a really brittle failure. And keeping in mind that we are talking about infrastructure, we should not increase this Q factor to higher values. So regarding the substructures, there's nothing special to say because we have substructures that can be designed in DC1, DC2, and DC3 according to Eurocode 812. And so there's nothing special. We can have typical steel structures, reinforced concrete structures. The only thing that we have to keep in mind is the differential displacement that we have to control. Regarding the behavior factor for vertical actions, it is again the minimum of Q and 1.5. So the Q that is taken for the horizontal direction of the seismic action, and 1.5 because usually the energy dissipation in vertical direction is somewhat limited. So this is more or less the concept. So we are not able to provide further, let's say, behavior factors for alternative materials. So this is out of the scope. We are not able to provide them because design codes for the other materials are not existing within the Eurocode concept. So the seismic loads that should be taken into account should take into account the spatial variability of the ground motion. And this is, let's say, due to, let's say, the traveling wave. So if the wave is traveling along the pipeline, we have to take into account local side effects and differences and changes in the soil properties, because if we have changes in the soil properties, we can easily see it in the design codes, the national design codes. We have different soil conditions. Different soil conditions will lead to different, let's say, shear wave velocities, and this will influence directly the impact. And the impact is mostly related to deformations here, because it is not that the pipeline is highly vibrating, so it's just moving with the soil. But we have to take into account these local side effects and incoherence. So we have different possibilities. So now we have in part 1.1, that is the first possibility. If we apply response spectrum analysis or time history analysis, we can use the concept of spatial variability that is given in chapter 5 of part 1.1. And here we can take into account site-specific response spectra at different supports along the pipeline. The alternative is that we use simply increasing factor, and the increasing factor depends on the soil conditions. So 10% increase for uniform soil conditions and shear wave velocities not higher or different, the difference in the shear wave velocity is not higher than 200 meters per second. 20% if we have non-uniform soil conditions and shear wave velocity is varying more than 200 meters per second. And if we have really, let's say, discontinuities, heterogeneous soil conditions, so jumping the stiffness of the soil, then we have to take into account it with 30%. So these numbers are related to the part for bridges, because it is a similar problem. So we have also long span bridges, and we have to take into account the incoherence and the spatiality of the soil conditions. So, and if we check this code, we can find similar numbers. So it was more or less adapted from the part for bridges. So to consider permanent ground deformations are fault crossings. So we need design rules for fault crossings. We need also to design rules for liquefaction induced phenomena. And here we have to distinguish between settlements, instability of foundation, and this lateral spreading. And I will go through these different types of phenomena on the next slides. And it's simply an exceedance of the load-bearing capacity. Then slope stability, landslides, and soil settlements. So these different, let's say, load cases are provided in the code and should be investigated by the engineer. So the verification should be done by the different limit states, and the limit state, the SD limit state, is the global stability. Then we have the verification of the pipeline itself. So there is a European Union code which is called EN 15994. And for unreinforced and reinforced concrete, we can take the Eurocode 2. And of course, the substructures of elevated pipelines should be also verified, but we have already the rules in part 1.2. The same for foundation. We have the part 5 with the load definitions, and also the anchorage systems are covered by part 1.2. So on top, we should verify probably the damage limitation state, and again, the same philosophy. If everything is in the linear range, then the damage limitation state can be regarded as satisfied. The OP limit state can also be investigated, probably together with the operator of the pipeline. And here, the main issue is that we have to check that the deformations will not influence the functionality of the pipeline. So I think for pipelines, it's much more important because it is usually they are part of the infrastructure, and the functionality after an earthquake has a higher priority as of a single building, of course. So this is more or less the concept for above ground pipelines. So now I will present the scope and design concept for buried pipelines. Again, we have the limitation that we have only continuous pipelines. So there are also pipelines with segments for water supply, but they are not covered here. We can probably apply the principles somehow, but it is not explicitly, let's say, incorporated in part 4. So we can have, again, steel and unreinforced concrete or reinforced concrete with or without pre-stress. And again, we have to take into account transient and permanent ground movement. So the effects that should be considered for buried pipelines are a bit different than the ones for above ground pipelines, because for above ground pipelines, we were able to carry out force-based design. Here, it's really a displacement based problem. So we will apply displacement along the pipeline, and then to carry out the design, not with Q factors, we are providing maximum strains. So the aim is really to calculate stresses or strains within the pipeline, and then to carry out the verification. So another specific problem is that we have to consider somehow the surrounding soil. That's quite clear, because the surrounding soil is in direct contact to the pipeline. How can we do this? So the easiest way is to take into account it with some simple models with springs, and to try to simulate the behavior in this way. So I will talk about this on the next slides. Furthermore, again, we have to take into account also the spatial variability. And again, we have some concepts available in the code, some simple ones with increasing factors, and some more advanced ones with considering the local soil conditions. Again, we have here different types of permanent ground deformations. So I don't want to repeat it, but they are similar as mentioned before. Here we can see that we have already some general, let's say, design considerations incorporated in the code. And these general design considerations are, let's say, constructive rules. They are provided in Annex C. So I really recommend to check Annex C, because there are really, let's say, reasonable approaches, and they can improve a lot the seismic behavior of a pipeline, especially close to faults. There are some proposals to improve the safety, and this cannot be substituted by a more refined or more advanced analysis. Furthermore, we have also to think about crossing of pipelines, and we need also to consider, let's say, the transition from the pipeline within the soil to a station on foundations, because then we have anchorage point, and then the differential displacements become more decisive. Again, we have also here the possibility to apply the concepts to other materials, but as I already mentioned, the alternative materials are not explicitly provided in our part 4. So here's just one example in Annex C. So we have one general design configuration that makes sense. So we see a fault crossing the pipeline. And what we can do is that we are using, let's say, a thicker wall for the pipeline close to the fault. And it makes also sense to put some coating to the pipeline to decrease the friction. So if we decrease the friction, we also decrease the influence of the moving soil to the pipeline, because then the soil is more or less moving around the pipeline. And this is really beneficial and will lower the maximum strain and the stresses that occur within the pipeline. So, and several of these, let's say, simple recommendations are given in Annex C. So I think it makes sense to start with these simple recommendations in order to solve several problems without highly sophisticated calculations. So if we have to set up a numerical approach, as I already mentioned, then we need a calculation model. And so if we check, let's say, the research activities, there are several different model approaches available. But we think within the code, we should try to keep it as simple as possible. And so the recommendation is to use a simple beam model with connecting springs, and then the springs should represent the surrounding soil. And each spring is associated with specific, let's say, load-bearing curves and load deformation curves in each direction. So this enables us to derive the spring stiffness for different soil properties and to connect this spring stiffness to the pipeline. So this is a really simple model. Then the question is how we can calculate this spring stiffness. So that is the reason for incorporating Annex D. Annex D provides some approaches for the calculation of the spring stiffness. It is an informative annex. Other approaches can be used, but there is one approach that is easily applicable, and we can take it from Annex D. And again, we have to distinguish between straight parts of the pipeline and the bending or the bends. But this model can easily apply to both, so to the bends as well to the straight parts, and we can connect it as we want. And it is a reasonable model for several reasons. So here it's just an impression how to calculate the soil structure interaction effect in terms of spring characteristics. In Annex D, you will find these load displacement curves for axial, transverse, horizontal and vertical direction, and you can easily calculate the maximum bearing capacity with respect to the friction, with respect to the diameter, and so on. And you can easily incorporate these relationships in your model, and this enables you to carry out the calculation without any problem. However, I have to say that we have to keep in mind that these relationships are nonlinear. So it is not, let's say, that easy to run such a simulation, because if we are entering the nonlinear range, we can also get some convergence problems, of course. However, there are alternatives to this model, and I think for straight pipeline, it is never required to use this model, because there are really simple approaches, simple analytical approaches available that can be used. So a simple strain analysis without considering the soil structure interaction, because usually the straight pipeline has really no problem. So the problem is always if you have anchorage points, if you have different or jump in the geometry, jump in the stiffness. So these are the crucial points, but the straight parts of the pipelines are usually not so decisive. So therefore, I can recommend to use this strain analysis that can be easily applied. If we have pipelines with straight parts and several bands along the pipeline, then we can use this model that I showed before, and we can easily apply nonlinear response history analysis, because we have to add displacements, we have to impose displacements to the fixed supports of the springs along the pipeline. And the advantage of this model is that it can also be used for permanent ground motion, because we can also impose with a static analysis the displacements to this nonlinear pipeline model. So I was talking about this strain analysis. So I think everyone knows that we can calculate the maximum axial strain, the maximum curvature with respect to PGV and PGA, and the apparent shear wave velocity. So we should keep in mind that the shear wave velocity is not the same as the apparent shear wave velocity, because this apparent shear wave velocity is the velocity of the traveling wave, and this velocity can be approximated to about 1000 meters per second. And then I can easily calculate the maximum strain curvature within the pipeline, within the straight pipeline, and then I can use the threshold that are given in the code, and then the verification is rather simple. We are assuming here that the strain of the soil is equal to the strain within the steel pipeline. So this is a basic assumption, but it doesn't hurt us, because the verifications are usually fulfilled for straight pipelines, and I really recommend to use these simple formulas. However, we can also carry out, and I'm showing here one situation with, let's say, two 90-degree bends and 45-degree. And here it is probably a bit more difficult. So here we can apply nonlinear response time history. How can we do it? We are taking this simple beam model with the spring characteristics, and then we have to apply different incident angles, because we cannot say in advance what is the decisive angle. And here, due to the fact that we have changes in the direction of the pipeline, so we have some effects like supporting effects due to the vertical part for the horizontal part of the pipeline and vice versa. And then we have to apply it along the pipeline. So it's a traveling wave. And what is written in the code is we should apply at the same time all three components in order to cover, let's say, the spatial effect of the earthquake. And the generation of the time histories can be carried out according to part 1.1. There is a special annex now to do this. So in order not to get crazy with all the influencing parameters, here it's also possible to simply increase the PGV and PGA values, as well as the design quantities coming from the time history analysis, by 20 or 30% with respect to the discontinuities along the pipeline. So not to, let's say, overcomplicate the problem. So I think time history analysis is complicated enough. So if we have some discontinuities, okay, so we can increase it by 30%. Again, this was taken, or this is close, let's say, to the approaches that were already developed nicely by the PT responsible for the bridges. So this is more or less what we can use for wave propagation. Now we have the permanent ground motion and permanent ground deformations. And here we have to handle fault crossings. So we are differentiating between normal slip fault and then strike slip fault. And this is shown here in plan and elevation. And the crucial point here is to estimate the fault movements, which are denoted as delta S and delta N. So either they have to be estimated with a site-specific investigation, or you can use NXE. I think NXE is quite useful. I'm not the expert for NXE, but I think Dimitrios can really answer all the questions because he did an excellent work there. And so this is, let's say, a possibility to extract delta S and delta N, at least for preliminary design. And then, okay, so later on we can also substitute it, or we can go on with these values. But the NXE, from my point of view, is quite helpful because from the practical point of view, usually the information are not available, and so you have to start somehow. And therefore, NXE is a really good, let's say, alternative to start. So if we have these fault crossings, we can easily calculate the axial and transverse displacements from the transverse slip fault delta S, and from the normal slip. And considering the incident angles and the angle between the crossing and the fault, the crossing or the fault and the pipeline, sorry. And then if we are able to calculate the differential displacements, we can, let's say, put it together, and we can calculate an average axial strain for each part of the pipeline, and we can assume on the safe side a wavelength which is incorporated here, and we can also calculate an effective unanchored length. So again, here we have to calculate the ultimate force per unit length, but this is also given an NXD. So we can easily reactivate NXD, which was already used for the spring characteristics, and we can use it again, and then it's quite easy to apply this formula. So the liquefaction induced phenomena, it's not such a big problem. So we can calculate the self-weight, then the covering soil, and then we have, let's say, the force that is acting upwards, and then we can easily calculate the pipeline with these forces coming from the liquefaction. The problem is here that usually it is not known. So what is the length of the liquefaction zone? So my experience is that you sometimes doing the inverse thing. So you are calculating the maximum length of liquefaction, and then you can compare it with what is expected at the location, and then usually, or hopefully, you will come up with the answer, okay, it is decisive or it's not decisive. But so this information is usually not readily available for all sites, but okay, so this has to be deeper investigated. So it seems quite easy, but the input parameter could be a problem. So then we have the lateral spreading. Just to understand what is happening, so here you see two figures. So you have on the left, you have let's say the problem with the bending of the pipeline, because the landslide is acting perpendicular to the pipeline, so you have bending stresses. Okay, how can we calculate the bending stresses? We need to have at least the width and length of the permanent ground deformation zone. And we need also the amplitudes. And then we can apply this, let's say, static displacement as a function to our straight pipeline. So this has to be done perpendicular to the pipeline to calculate the bending stresses for the pipeline. And there are two approaches for flexible and stiff pipelines that can be used. But we have also to consider the axial strain that is generated if the pipeline is installed in the direction of the landslide, which is shown here on the right side. And in this case, we have also two approaches to calculate the maximum strain. So these models are not complicated and they are really straightforward. And I think this is, let's say, an engineering approach. But again, from my point of view, it's not a problem to insert it in the formulas. It is a problem of, let's say, estimation of the input parameters, which cannot only be done by the structural engineer alone. Furthermore, we have to cover the slope stability, and the slope stability should be investigated along the pipeline. So slope stability can be a problem or cannot be a problem. Usually the slope stability should be verified along the pipeline, not because of the pipeline, because slope stability should be verified always. But probably it is not done for seismic actions along the pipeline. So that's what should be investigated, but it is not, let's say, part of this code, because slope stability, there are approaches that can be used with holding forces along, let's say, different circles of instability. And the last point are soil settlements, but these are really local effects, and we have to investigate it, let's say, on a really local level. And so there are no, let's say, general concepts. Again, we can make use of the simple beam model that I showed before. So similar to the combination of the actions, of the seismic actions for above ground pipelines, we need to incorporate the internal pressure, of course. And the funny thing is that the internal pressure sometimes has a positive effect, especially in the bends, because it will reduce the danger of buckling, because it will somehow smooth the pipeline. And of course, we have to take into account the covering soil, which is usually not so much, because for usual gas or water supply pipelines, we're talking about, I don't know, between 1.5 and 3 meters. Sometimes we have to cross the street. Okay, so then we are a bit deeper, but these are, let's say, extraordinary situations. And then we have to superpose it with self-weight and all the other variable actions. And if the inner pressure is acting all the time, then we have to apply it simultaneously with the seismic loading. So what should be verified? And this is quite important, because we are verifying the strain, because what was investigated for pipelines is that they can withstand larger strains because they are quite flexible. And we have here tensile strain in straight pipelines and in bends or T's. So why do we differentiate between these two different parts of the pipeline? So within the bends, we have always also some problems sometimes with compression. And so the compression can lead to buckling, to local buckling, and local buckling is always a problem that we have to consider, and therefore the threshold is quite different. And you can also see the compressive strain in straight pipelines. It's also reduced with respect to the T to the ratio of T to D. And in total, we have here welded steel pipelines, and we have also taken into account some ovaling effects, ovalization, that should be not greater than 2.5%. So these are the verification at the SD limit state. And there's nothing more to say about unreinforced and reinforced concrete or pre-stressed, precast, reinforced concrete pipelines. They have to be verified according to EN 1992. And we have also to check, that was also mentioned for the above ground pipelines, that the integrity is sufficient, and the ancillary elements connected to the pipeline should be safe. And we should also consider the effects of the ancillary elements on the pipeline. Okay, so here I think I can skip this slide because it is more or less the same as for above ground pipelines. So it's not obligatory to do it. We can do it. And in that case, we have to be in the elastic range, or we have to check the deformations for the functionality. So in the end, just a short view on NXE. So the NXE, it's an instrument to derive the surface displacements at the pipeline along fault crossing. And this informative annex can be used as an approximation. So it's not mentioned that it's exact, but it's a good estimation. And with NXE, we can really derive the required design differential displacements for the verification procedure that I showed before. So what was the motivation? To fill the gaps in the European codes and to provide a simple approach. And this is a more accurate probabilistic approach. And this is better than the deterministic approach that was used in the past. And it can be, let's say, applied quite easy with some geometrical information, crossing point, distance to the closest fault end, fault trace. And here you can see the pipeline, which is crossing the fault. And it is quite easy to get the values. So here are the steps. So first we have to identify the fault mechanism, then the length and fault crossing side, then the recurrence rate, which can be taken from a database. And then a really important step, we can recalculate the return period for a given fault displacement, or vice versa. And then it can be easily applied in our design concept. So this was more or less the story about the above and grid pipelines. And I think Charles is also joining now. So he's also able, let's say, to answer a question. And thank you. And we are ready to get your questions.
Thank you, Christoph, for jumping in instead of Charles, since he had the problem to join to the call. He joined and he used the time to answer the questions in the Q&A. So I think we can, since we are a little bit behind the time, we can skip for the next presentation, because I think most of the questions were answered by Charles, and the one that are not will be answered in written form. So then I will give the floor to my co-chair Fabrizio to introduce the next presenter.